Good day, students. This is a lecture on the resolution of ibuprofen. The ability to produce enantiomerically pure compounds is crucial to the fine chemical industries, the pharmaceuticals, agrochemicals and fragrances, etc. For instance, the revenue generated in the pharmaceutical and agrochemical industries by the production of enantiomerically pure products were estimated at $8 billion US, and that was 10 years ago. So imagine today, how much will you have? Most important in the pharmaceutical industry, where approximately 80% of the drugs currently under development are chiral. Enantiomerically pure compounds can be produced by one or two methods. The first method, enantiomerically pure compounds can be produced by one of the two methods. The first method is by a process referred as resolution. This is a process by which the two enantiomers of a racemic mixture are separated. The second method is by asymmetric synthesis. In an asymmetric synthesis, only one of the two possible enantiomers of the desired compound is produced. Asymmetric synthesis involves the use of chiral catalysts such as the chiral transition metal complexes or enzymes in key steps of the synthesis. The use of asymmetric synthesis has increased dramatically over the last few decades, but resolutions are still the most heavily used method in the large-scale production of enantiomerically pure compounds industrially. In this experiment, you will examine the resolution process by isolating the medicinally active S-positive ibuprofen enantiomer from a racemic mixture. So ibuprofen belongs to a class of pharmaceuticals referred to as non-steroidal anti-inflammatory drugs, or in short, NSAIDs. It is the active ingredient of Motrin, Advil, Nuprine, along with their other generic equivalents. Ibuprofen exhibits analgesic, antipyretic, and anti-inflammatory properties. And this makes it very well suited for alleviating minor to moderate aches, pains, and in fever reduction. Additionally, it has found use in treatment of rheumatic fever, rheumatoid arthritis, and osteoarthritis. Ibuprofen functions by strongly inhibiting the conversion of arachidonic acid to prostaglandin E2, which serves as a chemical signal for vasodilation. We call it inflammation, alright, in a more biological term. And of course, pain perception. Now it has been shown to the aryl substituted propionic acid NSAIDs to compounds such as ibuprofen, naproxen, or related compounds that of the two enantiomers, only one has the desired biological activity. For ibuprofen, the S-positive enantiomer has the desired pharmacological activity, while the R-negative enantiomer is inactive. With ibuprofen, the R-negative enantiomer has been shown to be non-harmful, so currently most commercial ibuprofen is sold in a racemic form. However, recent research suggests that optically pure S-positive enantiomer of ibuprofen is much more effective, and therefore several pharmaceutical companies are developing methods to produce the enantiomerically pure form of ibuprofen and its derivatives. There are several different types of resolutions. The first type of resolution discovered was the direct crystallization method. In this method, the compound in question forms half the crystals containing predominantly the R enantiomers and the other half containing predominantly the S enantiomer. The different crystals, if carefully examined, can be physically separated by differences in their appearances. Alternatively, If you have an enantiomerically pure crystal, this can be used as a seed crystal to precipitate the crystals of one enantiomer preferentially. This process was first used by Louis Pasteur in his groundbreaking resolution of tartaric acid. This first resolution greatly aided the development of our understanding of the stereochemistry of organic compounds and led to the discovery that many organic molecules have isomers that are non-superimposable mirror images. This type of resolution, however, only works with 5 to 10% of organic compounds. The remaining organic compounds tend to form racemic crystals containing equal amounts of both enantiomers, and thereby precluding the resolution using the direct crystallization method. Okay, so on this slide we're going to talk about the optical activity and a bit of history on that. Now, so this effect was first observed in quartz by D.F. Arango in 1811. And 4 years later, J.B. Buock found that the extension of rotation of the light depends on the thickness of the quartz plates that he used. So you see that these two are enantiomeric and they are not superimposable onto each other. They are never the same, so they crystallize in their own form and they won't aggregate together. You see, this is one of the crystal and the other one will grow differently. So likewise, you see one enantiomer can grow into so big and the other one just pales in size. Now he also discovered that other compounds such as the sucrose solutions are capable of rotating the light, and he attributed these optical activity to the certain features in their molecular structure we call asymmetry. And because of the research, he designed one of the first polaroscopes and hence formulated the basic quantitative laws of polarimetry. So how does it work? Normal monochromatic light contain light that possess oscillations of the electric field in all possible planes perpendicular to the direction of propagation. When light is passed through a polarizer, for instance the nickel prism or the Polaroid film, only light oscillating in one plane will leave the polarizer. And this linear polarized light can be described as a superposition of the two counter-rotating components which propagate with different velocities in an optical active medium. If one component interacts stronger than the other with a chiral molecule, it will slow down and therefore arrive later at the observer. And the result is that the plane of the light appears to be rotated. The other types of resolutions belong to a class of resolutions referred to as chemical resolutions, and these work by temporarily converting the two diastereomers. In these cases, the racemic mixture to be separated is reacted with a single enantiomer of second chiral compound, which what we call a resolving agent. Now the resolving agent is most often a single enantiomer of another chiral organic molecule, but in some types of resolutions it can be a biological agent, such as an enzyme or the transition metal catalyst. By reacting the two enantiomers of the racemic mixture with the resolving agent, two diastereomeric compounds will be formed. Unlike enantiomers, diastereomers do not have identical physical properties. Melting points, boiling points, solubility, chemical luminescence, etc. If these differences in physical properties are large enough, they can be used to separate the two diastereomers. After separation, the two diastereomers are converted back to the two enantiomers by the removal of the resolving agent. Right, so here in this figure, you can see the general overview of the process. Now in this experiment, you will use a chemical resolutions, part 1 to 4, in the procedure section. Is used to separate the two enantiomers present in racemic ibuprofen. Following this, a direct recrystallization resolution may be used to further improve the optical purity of the medicinally active S positive enantiomer of ibuprofen. And that's part 6 in the procedure section. Now in part 1 of the experiment, the enantiomeric ibuprofens are reacted with a resolving agent to produce 2 diastereomers which can be separated. A good resolving agent has several requirements. First, it must be chiral. It has to be, right? If not, how do you form a diastereomer? And it must be available as a single enantiomer. It can't be a racemic mixture, right? There's no point if you introduce another racemic mixture, then you got so many products. What's the point? Think about it. Now second, this resolving agent must react with the compound to be resolved to form diastereomers with significant differences in their physical properties. What it means is, if I form the 2 diastereomers, of course they will show differences in their physical property. But what if both melting point or the boiling point are too close for separations? It is not effective. If the melting point and boiling point differ by about 2 degrees Celsius, how are you going to separate them using distillations? And third, the reaction that form diastereomers must be reversible so that the compound being resolved can be recovered at the end of experiments. You don't say, if I can't get back my original compound, then what's the point of having this resolving agent then? Right? We are forming something new and then we change the pharmacological properties of the drug. Now for this resolution of ibuprofen, the S-negative alpha phenylethylamine meets these criteria. Ibuprofen is a chiral carboxylic acid. It will undergo a reversible acid-base reaction with the basic S-negative alpha phenylethylamine to produce 2 diastereomeric salts. And these 2 salts have very different solubility properties which makes them easy to separate. 1. The SS ibuprofen phenylethylammonium salt is insoluble in water and quickly precipitates from solution. The other RS ibuprofen phenylethylammonium salt is water soluble and stays in the solution. You can see the figure here. It should give you an overall image of what I'm saying. Once the diastereomers are physically separated from each other, the resolving agent must be removed to yield the individual ibuprofen enantiomers. This is accomplished in steps 3 and 4 in the experimental section. Now this is simply done by adding a strong acid to the diastereomeric salts. This will cause the ibuprofen to be protonated and convert itself back to its neutral form. Neutral ibuprofen is not water soluble because the interactions are not very favorable, and it will separate out of the solution. It can then be recovered by extraction with a moderately polar organic solvent such as MTBE, methyl terbutyl ether. Once the separated enantiomers are isolated, the effectiveness of this separation process is determined by comparing the optical rotation values of your samples to the literature value of optically pure ibuprofen, and that's all housed in part 5 in the experimental procedure. When you look at the results, you will see that the optical purity of the S-positive ibuprofen is higher than that for the R-negative enantiomer. This is to be expected for several reasons. First, whenever solubility is being used to separate the diastereomeric salts, the one that precipitates from solution usually has a better optical purity than the one that is soluble and stays in solution. This is because the less soluble diastereomer still has some solubility in the solvent being used, and this causes some of the less soluble diastereomer to remain in solution and contaminate the more soluble diastereomer. Second, in the procedure, subsequent steps such as recrystallization were used to purify further the less soluble diastereomeric salt. This was not done for the soluble diastereomeric salts. Take note. In the industry, the R-negative enantiomers is recycled by chemically converting back to a racemic mixture, which is then again submitted to the resolution process. This means that there's no reason to waste a considerable amount of effort to get it optically pure. Should you have any more queries, you can always check for these references and read up more. Thank you and have a nice day. Now students, I would like to emphasize on safety, and this is an incident that you can learn. You know, when an emergency happens, maybe you see a fire, somebody's on flame, please do not do what you see in this video the gentleman's doing. See that everybody is so chaotic and everyone is so scared, and yet this guy is so cool and calm, swag, and just take out his camera phone, walking and taking photos. You see, too nonchalant. This is not good. You should really pick up the phone and call somebody, call the campus security, call the emergency number. Okay, so please don't do this. It is your responsibility, and also help each other around. Remember, safety is first.